Hello, I'm Isabel with High Tech Design Safety, here with the presentation for you on laser safety in semiconductor manufacturing equipment. You are looking for certification support, and we at High Tech Design Safety specialize in certifying industrial machinery and semiconductor process equipment with more than 1,400 successful projects to our credit. Our process is designed to provide support and certification guidance throughout every stage of the project, helping manufacturers simplify the path to market. Lasers play an important role in semiconductor manufacturing equipment. They are used for precision measurement, feature detection, marking, cutting, annealing, and other specialized processes. However, the concentrated energy that makes lasers useful can also create significant hazards for personnel, equipment, and facilities. In this video, we'll cover the major laser hazards, how laser classifications affect risk, and the controls manufacturers can use to create safer equipment. Eye damage is one of the most serious laser hazards. Exposure can cause severe injuries, including permanent vision loss or blindness. Lasers can also cause skin and UV-related injuries, but the risks extend far beyond radiation exposure. Laser equipment may introduce electrical shock, thermal burns, fire hazards, and exposure to smoke, dust, or particulate generated during processing. A complete laser safety strategy needs to consider all of these hazards. Laser classification helps determine the level of hazard and the safety measures required. Class 1 lasers generally present very low risk under normal operating conditions. Class 2 lasers emit visible radiation and rely partly on the natural blink and aversion response. Class 3R and 3B lasers introduce greater eye and skin hazards, while Class 4 represents the highest hazard category. Class 4 lasers can cause severe injuries, create dangerous reflections, ignite materials, and generate hazardous process byproducts. Another important consideration is the difference between the embedded laser and the classification of the overall laser product. For example, a Class 1 laser product may contain an embedded Class 4 laser. During normal operation, the higher powered laser may be safely contained. However, maintenance or service activities can expose personnel to a much higher level of risk. Manufacturers need to understand both classifications when evaluating equipment safety. For higher powered lasers, protective housings are one of the most important engineering controls. These housings contain hazardous radiation and help prevent exposure to personnel and the surrounding facility. Designers must consider both the intended beam path and the potential unintended paths caused by reflections, loose optical components, broken materials, or objects left inside the enclosure. Beam stops, shutters, light-tight joints, and properly designed access points can all contribute to safer containment. Protective housings often work together with safety interlocks. If a door, panel, or access point could expose someone to hazardous radiation, an interlock can prevent continued operation under unsafe conditions. Depending on the system, additional controls may include emergency off functions, manual resets, key controls, and laser emission warning devices. Facilities should also establish procedures for training, authorized access, incident reporting, maintenance, and other laser safety activities. Personal protective equipment provides another important layer of protection. Laser safety eyewear must be selected for the wavelength and power of the specific laser. Eyewear designed for one laser may not adequately protect against another. Higher powered applications may also require protective skin coverings and non-combustible clothing. Medical surveillance, including baseline eye examinations, can provide additional support for personnel who regularly work around laser systems. A laser safety evaluation should never stop at radiation exposure. Laser systems may use high voltage power supplies and contain stored electrical energy. Equipment and workpieces can also reach temperatures capable of causing burns. Cutting, annealing, ablation, and marking processes may generate smoke, dust, and particulate that require effective exhaust systems. These risks also need to be considered during maintenance, service, and equipment decommissioning. Several standards provide requirements and guidance for reducing laser hazards. IEC 60825 addresses areas such as laser classification, protective housings, measurements, and manufacturer requirements. Other relevant standards include ISO 11553 and the ANSI Z136 series. For semiconductor manufacturing equipment, SEMI S2 also provides laser safety requirements and evaluated guidance. The standards that apply will depend on the equipment, laser system, application, and intended market. Laser safety in semiconductor manufacturing involves much more than preventing direct exposure to a beam. Manufacturers need to consider classification, beam paths, protective housings, interlocks, PPE, electrical hazards, thermal hazards, ventilation, and service activities. Addressing these hazards early in the equipment design process can support safer machinery and a stronger path towards compliance. High-tech design safety helps semiconductor equipment manufacturers identify safety requirements, evaluate hazards, and develop practical strategies for equipment conformity and compliance. If you found this video helpful, be sure to like, subscribe, and visit the HTDS website for additional resources covering laser safety, industrial equipment compliance, CE marking, semi-standards, and much more. Thanks for watching, and we'll see you in the next video.